Example 5.3.2. All right, this one says you are purchasing a car priced at $16,484.30. The dealership is offered to let you buy the car today in exchange for payments of $402.43 at the end of each of the next 48 months, the first payment due 1 month after taking out the loan. What is the monthly effective rate on this loan? What is the quoted APR, annual percentage rate? What is the EAR, or effective annual rate? Okay, so we've got 3 questions to answer with this one. Luckily, all 3 of them are tied together, and it's not much to get from one to the other. We do have a time value money problem, so we're going to use our 3-step process to get through this guy, where we're going to start with the timeline so that we can map out the cash flows and see what we're dealing with. And then from that cash flow map, once we've got the timeline, we can figure out what type of cash flow we're looking at. That's step 2, to identify the type of cash flow. And then in step 3, once we know the type of cash flow, we can figure out which tool we want to use to evaluate that cash flow. We'll know what tools are available to us, and we can pick from them. So let's start by mapping this guy out. So today, we're going to buy a car, and we're going to map out the cash flows for the loan. So we're going to buy this car. They're going to give us a loan for $16,484.30. And from the perspective of the borrower, we're receiving, if we just look at the cash flows from the loan, we're going to have a cash inflow of $16,484.30. Of course, we're not going to keep that cash. We're going to exchange it for a car that is worth that amount. So we're going to receive something of value that's worth about $16,484. Once we do that, we promise to make monthly payments on this loan. That is, we receive the car today. 1 month from today, we're going to pay $402.43. So we're going to have a cash outflow, recorded as a minus, to show that it's cash outflow, of $402.43. 2 months from today, we'll do the same thing again. We'll have a cash outflow of $402.43, and we're going to continue that pattern. So I'll just do our broken line here and our ellipses to say this pattern continues out to, or for 48 months. At the end of 48 months, we're going to make our final payment of $402.43. And the one variable we don't know is what is the interest rate on this loan. So once we consider those cash flows, what is the actual interest rate that we're paying, both the effective monthly rate and the effective annual rate, and also the quoted interest rate on the loan, the APR. All right, so step 2 is to identify the type of cash flow that we're looking at. We have a lump sum cash flow up front at time period 0, followed by a level stream of cash flows that ends a finite stream of cash flows. Okay, those level cash flows over time, that is the definition of an annuity. We've got equal cash flows at regular intervals that stop at some point. The only question is what type of annuity. We have 3 of them. If we look at our cheat sheet, we have an ordinary annuity with cash flows at the end of each period. We have an annuity due with cash flows at the beginning of each period. So each cash flow is just bumped up. And we have the first one at time period 0. Whereas in the ordinary annuity, the first one was not today at time period 0, but rather at the end of the first period. And here they are at the beginning of the period. And then we also have a growing annuity where the cash flows grow at a set rate, or they could shrink at a set rate over time. They just change at a set rate over time. Well, our cash flows in this problem are not growing, so the only question is, are they happening at the beginning or the end of the period? Well, if we look at these timelines in the examples and compare that to what we've got, we see that the first cash flow, the first payment, is happening at the end of month 1. In fact, in the problem it says the first payment is due 1 month after taking out the loan. And so that first payment is at the end of the month. So we are dealing with an ordinary annuity. Once we know that we're dealing with an ordinary annuity, it is time to select our tool that we're going to use to evaluate it. And when we're dealing with ordinary annuities, we have three available to us. We've got the present value or future value of an ordinary annuity formula. We've got the time value money keys in a financial calculator, and we have a spreadsheet. We're going to skip over the spreadsheet just because that is not usually available on an exam, and we want to practice the things that we will have access to. So that leaves us with the formula or the financial calculator. Let's talk about the formulas for just a second, and then we're actually going to jump right to the calculator, but I do want to talk about why. The first thing to note is we would want to choose whether we use the present value of an ordinary annuity or the future value of an ordinary annuity formula. Either one will work just fine. It's a question of what information we're given and which one will require the fewest number of steps in order to use. With this particular problem, we are given the present value of this annuity. We know the loan amount. So what we would want to do is select, if we were going to use the formulas, we would select the present value of an ordinary annuity formula, plug in everything that we know, the present value being, in fact, let's just write it out so we can see what we're looking at here. We're not actually going to go through and solve it. The present value of an ordinary annuity is our payment divided by the interest rate times the quantity of 1 minus 1 over the interest rate. So we'll just have both of these up here so you can see that I'm just copying the formula. So the present value is equal to the payment. And importantly, in this case, we're looking at the present value at time period 0 and the payment at 1. The payment is always 1 period after the present value we're looking at. Divided by the interest rate times 1 minus 1 over 1 plus the interest rate raised to n, where n is the number of payments or the number of compounding periods on this loan. Okay, let's plug in what we know and see why it would be difficult to use this formula as I fight with how my screen's oriented here. Okay, so the present value is $16,484.30. The payment we know, that's $402.43. The interest rate is what we're looking for, so that's R. One plus R, and then N is the total number of payments or the total number of compounding periods. That's 48 in this problem. So if we were going to use the formula, we would need to solve for R here. Well, we have a problem. We've got R by itself down here in the denominator, but then we have R within parentheses, 1 plus R, and then raised to the 48. There is not a way to use algebra to get R by itself on the left-hand side. We can't solve for it. The only thing that we could do is kind of look at the problem and make a reasonable guess at R, plug it in, and see if it made the equation true. So maybe we would start at 10%. We plug in 0.1, see if it balanced out. If it didn't, we would adjust our guess based on what we got and try again. And we would just have to keep going until we got it close. You can solve it that way. It just takes quite a while. So it is much faster to use the financial calculator or the spreadsheet. And of course, we're just going to look at the calculator here. So let's look at the time value money keys. And the way I like to do these is to actually write out the keys in the same order they appear on the calculator. So that's N, I over Y, PV, PMT, and FV. I write them vertically just because that's the habit I got into when I was learning these problems. There's no reason you have to do that. You can write it out however you want. I just encourage you to find a way to work these consistently every time to make sure you don't miss something. Okay, N is the total number of payments or the total number of compounding periods. That's exactly the same as what we would put in for N in the formula. And it is the final tick mark on our timeline. We have 48 total payments, so N is 48. I over Y is what we're looking for, so I'm going to put something that at least looks a little bit like a question mark right there. Present value is the amount of the loan, or what happens with the cash flow keys, PV, PMT, and FV. What we put on those values in the calculator are the cash flows that happen in the corresponding parts of the timeline. So present value is what happens at time period 0. That is $16,484.30. In this case, that also happens to be the present value of this annuity, but that's not always the case, as we'll see with the future value here in just a second. Payment, the reoccurring payment that happens over and over again, is $402.43. Now I recorded that present value as a positive number, so that means I'm telling the calculator that's a cash inflow to me. It's coming in, and the payment is moving in the opposite direction. So I received something of value. It came to me of $16,484.30, but then I'm going to have to pay or have a cash outflow of $402.43, so I'm going to record that as a negative. So the calculator knows the relative direction of those cash flows. All right, future value, we're actually going to record a 0 here. Not because the future value of this annuity is 0. It's not. It has a future value. But what we're putting on these cash flow keys is what happens on the timeline. And future value is what happens at the end of our timeline. Any cash flows out here. We have already told it that we're going to get 48, or we're going to make 48 payments of $402.43. So that's already on there with n equals 48 and payment equals $402.43. We don't have any additional cash flows in addition to that last payment, so we're going to record a 0 there to tell the calculator there isn't anything extra that happens. Okay, let's put these in and solve them. I'm going to start, as always, by clearing out the time value of money by hitting second and clear TVM. That records 0 on all 5 keys, and then I'm going to work left to right to make sure I don't miss something. N is 48, so I'll type in 48, and N. I over Y is what I'm solving for, so I'm going to skip over that for now. Present value is a positive $16,484.30. So I'll type that in and then press PV to store it. Payment is $402.43. I'll press the plus minus key to make it negative, and then press payment to store it, and future value is 0. Now when I cleared it out, it should have entered a 0 there, but just to be sure, I'm going to go ahead and type 0 and press FV to store it. All right, I have 4 of the 5 variables in there. The calculator can solve for the 5th, which I can do by hitting compute I over Y. All right, and we're going to get a value of 0.6667. And that's already in percentage format, so it's 0.66, probably repeating percent. Now, here's the part that we have to get comfortable with in Chapter 5. It's the wrinkle that this chapter introduces. This is no longer an annual rate because these cash flows aren't annual. The interest rate that we plug in for I over Y, or that we solve for on I over Y, is going to be the effective rate that matches the frequency of the cash flows. So in this case, we've got 48 months. All right, and the payment is happening monthly. And so the interest rate that the calculator gave us is the monthly effective rate. All right, and the terms on those 3 keys, these 3 keys are always going to match, N, I over Y, and payment. If N is in months, then I over Y and payment needs to be months. And really what determines that are the cash flows themselves. The payment key, what's happening on the payment key is what determines what is happening on the N key and the I over Y key. In this case, the payments are happening monthly, and so the N has to be the number of months, and the I over Y is going to be the monthly effective rate, which I think, let me look back, I think that was the first question we had to answer. What was the monthly effective rate on this loan, right? So that was the first thing we were looking for. And that is already in percentage format, so that's 0.6667%. All right, so we got the first question answered. The next one is, what is the quoted APR? All All right, now this one is getting at the definition of APR, and that has a particular formula definition. If we look at our formula sheet, I believe that's the first formula for Chapter 5. It is. APR is defined as APR equals R times M. All right, R times M. Of course, those are just letters. What the heck do they mean? APR is annual percentage rate. R is the periodic effective rate that matches the frequency of the cash flows. So for example, in this problem, we've got monthly cash flows. So this little r is the monthly effective rate. If we had quarterly cash flows, this would be the quarterly rate. If we had annual cash flows, this would be the annual rate. M is the number of compounding periods per year. So for this problem, since we have monthly payments, that is 12 payments per year, or 12 compounding periods per year. So the APR for this problem, which is what you would see stated on your loan documentation, is the monthly effective rate of 0.6667, and that's going to be 6 repeating. My calculator is just set to show 4 decimal places, but I will write it like that. It's that monthly effective rate of 0.6 repeating percent times the number of compounding periods per year, which is 12. So our APR for this problem, and I'm going to eliminate rounding errors here by using this value that's already on the display. Although it's showing me 4 decimal places, it's worked out to about 13. So I'm not going to type this in again. I'm going to use what it has stored internally, and I'm just going to say times 12. And that will give us an even 8%. All right, so the monthly effective rate is 0.6 repeating percent. The annual percentage rate, which is what you would see actually stated on your loan, is 8%, which we find by just taking the monthly effective rate and multiplying it by 12 months per year, number of compounding periods per year. Okay, the last question we want to answer is, what is the EAR, or the effective annual rate? Now, with the APR, all we did was take the monthly effective rate and multiply it by 12. So what we have ignored here are the effects of compounding. Of course, every time we make a payment, there's going to be a little bit of interest in that. And then if we have another payment within the year, we're going to be paying interest on interest. And the lender is going to be earning interest on interest. And that compound interest is completely ignored by the APR. So very frequently, we are interested in what is the actual effective rate that we are paying. And there is a formula to move back and forth between the annual percentage rate and the effective annual rate, and it's this guy right here. So the effective annual rate is equal to 1 plus the APR divided again by M, the number of compounding periods per year, and raised to the M, minus 1. Now this should look pretty familiar. In fact, for just a second, let's take this definition of APR right here that's above it. And I'm going to do this for the sake of showing that we've actually already seen this before. It's performing a function that we've already used before. If I take this APR equation and I solve for R right here, the periodic effective rate, what I'm going to do is divide both sides by M. And so R, the periodic effective rate, is equal to APR divided by M. That means I could substitute in right here APR over M. I can substitute in R, or our periodic effective rate. So I could rewrite this as 1 plus R raised to the M. Now this guy right here should look real familiar. That is our interest rate factor. That is how we compound and find future value, right? It accounts for the effective compound interest over time. That is exactly what this annual effective rate formula is doing for us. So we can use, these are equivalent, these two statements. You don't have to use both, but we'll go ahead and use both of them just to see how it works. So if we're using the AR formula as it is on the formula sheet, we're going to do 1 plus our APR of 0.08, because now we're doing math with the interest rate, so we need to convert it to a decimal. So 0.08 divided by 12, where 12 is the number of compounding periods per year, or the number of payments per year. Those two are equivalent. And then we're going to raise that to the 12 minus 1. Let's go ahead and calculate that. So 1 plus 0.08 by 12 equals, raised to the 12, so y to the x, 12, equals 1.083. Then we need to subtract 1 from it, so our effective annual rate is equal to 0.083, or 8.3%. All right, just for the sake of demonstration, I'm going to use this second variation of the EAR formula where we just plug in the monthly effective rate and see that we come out with the exact same answer. So our EAR is equal to 1 plus, in this case, this is going to be the monthly effective rate, or that 0.666 repeating percent, expressed as a decimal. It's going to be 0.0067 roughly, and I'm going to use a more exact value here. Raised to the 12 minus 1. All right, now to make sure I get an exact value here and I eliminate, or a more exact value here, and eliminate some of the rounding errors, what I'm going to do to find that R, all right, I need to take the APR and divide it by M, or the number of compounding periods per year. So that is 8% is my APR, 0.08 expressed as a decimal, divided by 12, equals, there's my 0.0067, which is the same thing I have written here, but the calculator is just approximating the display. It actually has this worked out to about 13 decimal places, a much more precise answer than what it's showing me. So while this is on the display, I want to use that more exact answer. I'm just going to leave this on here rather than typing it in and say plus 1 equals. All right, and then I need to raise that to the 12, so I'll press y to the x, 12 equals, and then I need to subtract 1 still, minus 1. And I get the exact same answer of 0.083, or 8.3%. All right, now of course you don't need to use both. I just wanted to demonstrate what was happening with that APR over M, what that thing actually is. That's the periodic effective rate that matches the frequency of the cash flows, or the frequency of the compounding periods, or rather the number of compounding periods in the problem. You can pick either one of these, of course. The APR over M version of the formula is what's on the formula sheet, so feel free to go right for that. And that is it.